everybody. I have the pleasure today to introduce another friend, a friend of almost 40 years, Mejdi Azaiez. Mejdi Azaiez is a full professor at Polytechnic Institute of Bordeaux. He was assistant professor at the University Paul Sabatier in Toulouse, and he's actually the head of research department TREFL with 50 permanent researchers and 6 engineers. Mejdi Azaiez is a specialist in computational fluid mechanics and applied mathematics. He mainly dedicates his research activity to the numerical resolution of Navier-Stokes equations. He produced more than 90 scientific journal publications and supervised 26 PhD in mechanics and applied math. The research interests of Mejdi Azaiez are reduced data, partial fractional differential equations, high-order methods for incompressible flow, high-order methods for Darcy flow and porous media, phase and change material, inverse problems, heat and mass transfer, Hodge, Helmholtz decomposition, and spectrum computational of operator under constraints. The talk of Mejdi Azaiez today concern a variant of scalar auxiliary variable approaches for some nonlinear problems. Thank you, Mejdi, to accept our invitation, and you are welcome.
Okay, good evening, everybody, and thank you, Nabil, for this nice presentation. I would like to say just a few words in French, and after, of course, I switched to English. As you can see, my favorite language, first Arabic and second French, and that's why, to answer to Nabil, I will prefer to say it in French. Nabil, merci beaucoup pour l'invitation, et je tiens beaucoup à te remercier pour l'organisation de cette série de conférences par Zoom et par web. Je pense que dans la vie, il ne suffit pas d'avoir des idées, il faut pouvoir les faire vivre. Et tu fais vivre ce séminaire avec beaucoup d'énergie, mais tu as parlé de 40 années. Moi, je dis que s'il y a une valeur constante chez toi, c'est l'énergie. Donc, je sais que tu ne manques pas et tu n'en manqueras pas, donc bravo. Okay, now I switch to English to give my presentation. This is investigation I made because I met this group of Chinese colleagues and friends. And they are quite specialist in this techniques, and they are producing a lot of results on the subject. And on the other hand, I am a member of a mechanical engineering group. And inside this group, we have some colleagues who are working and collaborating around the subject of how to store energy using material and more precisely, phase change material. This is the motivation of this work. And let me try to go. Okay, this is the sketch, this is the plane. Some words about the motivation. And after I will propose and present what is one definition of the phase field model. And after I will present you a new technique. This is not so new because we are just considering one idea published by one of the group of Chinese colleagues. And we improve it thanks to my student, Mr. Hu, sorry. And after with Mrs. Yao, we adapt this technique to improve the numerical resolution of Navier-Stokes. This is the plane. I hope I can go till the end of the objective of this presentation. First of all, you know, we have many possibilities to follow an interface. And in our case, we have a real moving interface. And in our case, the interface, think, for example, that we have a glass, one ice, and you put the ice in the water. The ice will go from the solid state into the liquid. And the interface between the solid and liquid is moving and is disappearing. We are the situation with, let's say, the interface behind it, we have physical phenomena. And as soon as your interface is respecting or respects to some physical phenomena, I think one of the well-adapted method is to go with phase field technique. By the end, phase field remains something that will be with two values, 1 or 0, that can be -1, 1 if you rescale it as I do here. But in our case, in one phase, for example, solid is going to be 0 and liquid is going to be 1. And in between, it will take some value. And the function itself is continuous. It goes from 0 to 1, and it takes many values in between. And the epsilon, as I wrote here, depends on the interfacial width between the two phases. And now the question, and the fundamental question, what equations, what model should we solve to adapt the phase field from one moment to another moment? Okay, let me please give an example. I spoke about phase change material, and one of the easiest and one of the, let's say, modest model is to solve the heat equation coupled with the phase field. Imagine that you start with solving, you have a repartition of the phase field. Okay, you start with some phase field, solid, liquid, and you solve the temperature equation. Once you have the temperature, you solve a new equation of phase field. The new equation phase field will help you to design where we have the conductivity of the solid, where we have the conductivity of the liquid, and you solve again the temperature. So you couple both, and each time step you have new position of the interface, new position of the solid and liquid, and once again you solve the temperature. I will be back to this example at the end to show you some simulation. The parameters here, epsilon, tau, and all this is the classic for thermal equation, capacity, heat latent, and here tau is related to the relaxation time to equilibrium. It helps us to control the motion of the interface too. Epsilon represents the interface wide, as I said before. This is important. This is the potential function, which is non-linear. It is almost non-linear. And behind this, you have to put the right thermodynamic, you have to put the right description of the physics that you can model in the interface. Please think solid, liquid, in between we have phase change, and there you should work with people who are enough strong to help you to write the best definition of the physical phenomena inside. Once you succeed this description, you are in the well position to produce nice physics. Okay, I spoke about gradient flow model. It's a family of flow model for which the equation of the phase field is described thanks to this equation. It means that when you vary your phase field in time, you are equal minus gradient A of phi, and A of phi is the free energy functional associated with the physical phenomena. I will give you some examples. Once you go with this family of a gradient model, be sure that you can ensure this equality, this equality, and more than equality. This result is quite interesting because behind you have the energy dissipation law, which is amazing for our goal, our objective to solve this equation. Okay, now I would like with you to fix some example. I will play with two families. The first family is going to be the definition of free energy function. I mean, the relationship between the energy function and the phase field is going to be a sum of this part and this part. This is behind you have the description of the physics inside the interface. And here we have the competition between the two aspects, solid and liquid. This is one example of model. For some situation, we can call this Allen-Kahn model. I'm going also to play with this other definition of free energy function. And this is given by the Laplacian, not the gradient. And the function here is not applied to the scalar, which is the phase field, but it's gradient. Now we are here in the family of what we call cannular. Cannular here, Alan here. And once again, you have the epsilon. And for example, for this family, I will mainly consider this nonlinear function of capital F. And for this family of MBA, what is molecular beam epitaxial model, I'm going to play with this definition. This is definition in one part, it is MBA with slope selection. I can means, as it is said, we can select the slope, and without slope selection, we will consider the second definition. So, okay, you don't need to retain this because when I will use one, I will recall it for you. Okay, this is the keystone of the method. We start the model with capital A, and I would like to propose something that I will call E alpha. Alpha, it is here, and it takes the place of epsilon. So I keep the same definition. If you come to me with 2.3, I will consider E alpha the same thing, but instead of epsilon, it will be alpha. And if you come with cannular, which is 2.4 in the previous slide, it will be this quantity. Epsilon becomes alpha. But for me, it's a family of functions, and I will take the liberty, I will take the opportunity to play with alpha. Alpha can be 0 and can move from 0 to epsilon power 2. Epsilon power 2, E alpha becomes the initial functional energy function. Note that I take this hypothesis. I mean, I will consider that it's always possible to consider a constant C such a way this quantity becomes strictly positive, not positive, but not 0. This is some kind of material tools that I'm going to use now to propose the scheme. Okay, we need 2 minutes to planter le décor. It means that to keep the problem in mind. My phase field problem is going to be written as follows. I have every time to solve the derivative of the phase field in time. It is equal to GH mu. What is GH? GH, it is first mu, it is minus epsilon Laplacian phi and the derivative of f of phi. What is the difference between GH and another GH? In one case, GH is going to be minus identity and it's going to be Laplacian. It is one way to conduct two models in parallel. When GH is minus identity, you are Alan-Kahn model. When GH is a Laplacian, it means that in this equation, we are going to play with B Laplacian because we have a Laplacian of Laplacian. We are with cannular. Alan-Kahn means this case, and in this case, my boundary condition is going to be Newman. If I go with cannular, my boundary condition is going to be a boundary condition that we use to apply for B Laplacian. For instance, it's going to be flux and this derivative. This is some detail to complete the problem that we are going to solve. In some case, the boundary condition will be for me periodic as well. So this is the problem now. And if you go with the literature and you ask the literature about different way to approximate in time and in space this model, the literature is very huge. And the objective, dear colleagues, is to be able to propose as unconditional stable in time as possible. And it's always also to propose a scheme that can be efficient when epsilon goes to 0. I mean, let's say when epsilon is small, it means that the length of the zone between solid and liquid, where we have the phase change phenomena, it becomes very sharp. I mean, our material should be able to be unconditionally stable in time, to be accurate in the space, and to resist to any choice of epsilon. Because in many physical situations, epsilon can be really something like 0.001 and maybe sometimes less than. Okay, so this is the idea. This idea comes from this paper of my colleague and friend Jia Shan, and he proposed a nice idea, but for his paper, the idea was alpha equals 0. He started with alpha equals 0, but this method that we reconsider with my student and we extended to another one looks more interesting in the sense that it is more robust to cover more choice of epsilon. In his case, epsilon, it's okay, but it should be not very small. I mean, the quality of the approximation suffers from point of view of epsilon. This method will improve a bit this question. Okay, let's focus on the idea because it's really nice idea. I mean, let's consider this scalar. Please remember that this quantity E alpha, it is the integral on space. So we have now a new function that we call the auxiliary scalar auxiliary function. It depends in time. It is the square, Racine square of the quantity here. Remember that this is strictly positive, and you now understand why it is positive, and I have to derive it. Since I have to derive it, I will take care about the fact that it should not be equal 0. That's why I suppose that every time it's possible to fix C0 such a way, all this becomes strictly positive. And now let me go back to the initial problem. Remember, it was something like this. What I'm doing now, I'm doing to rewrite it exactly identical. But please have a look. This quantity, which is here, I wrote it here, but this is and this is remains the same. It means that it is equal the denominator. It means that this is really equal 1. 1 minus 1 is equal 0. So it means that this term is 0 and this term is 1. When you say that term is 0 and this term is 1, it means I am exactly the previous scheme. So I do not change the scheme. I just make some kind of additional term, which is fusion term, and I'm going to multiply the nonlinear term, which is let's say the hard question of the problem, the nonlinear term, by multiplying it by something that looks 1, but I'm going to perturbate it. I'm going to change the value of 1 to make it small to 1, because I'm going to add an equation coming from this. It's not really complicated to derive this quantity, and keeping in mind the definition of E alpha, when you derive in time with your take 2 minutes with paper and pencil, and you can prove that this quantity, when you derive it, you have this equation. The derivative in time of this 2.8 is exactly this quantity. Okay, so why I'm doing this? I'm doing this because now I'm going to switch from the continuous problem exactly equal to the previous one. Using time scheme approximation, I'm going to perturbate, and I'm going to make this not equal 0, but close to 0. Let me show you. First order scheme. Sorry. So I derive in time here. It is Euler 1, nothing to say about. And I have, okay. Now this is what I'm proposing to solve. It is this operator. This quantity is implicit. And you see here, it becomes explicit. And please look that the nonlinear term is explicit. It is multiplied by something. Everywhere we have n. N means I am in previous time step. N plus 1, I am the current time step, and this is the unknown. It means that to solve mu n plus 1, it means to solve phi n plus 1, I need Rn plus 1. But Rn plus 1 is going to come from the equation on R, which is here, that I approximate first order 2. And you can see that here also I have this unknown. So they are coupled. And once again, remember that I'm conducting 2 models in the same time. Alan Kahn, Hillary, nothing changed, just to think about. And now this scheme, it's really technical, but nothing complicated. You can prove that this scheme is unconditionally stable in the sense that the following discrete energy law holds. This is, you can see, and what is amazing in here, I mean, in the limit, if my E alpha alpha takes epsilon power 2, this quantity becomes 0, this quantity becomes 0, and I see that Rn plus 1 is lower than, and this is, it becomes negative. And R, please, R is the error between the exact, the approximating solutions. So things looks nice, unconditionally stable, and we see that everything is come from this theory. Okay, I have a second order version. Just make BDF2 here. And once again, I have to adapt. This is explicit. Okay, this is explicit. So it means I just have to compute. And the only implicit part is Laplacian. And this one, I will tell you how to do to decouple these two equations. Everything written with n plus 1 over 2 for an extrapolation. And for instance, I choose Adams-Bashford, and very natural. So also for the scheme, I can prove an unconditional stability theorem. For this kind of problem, it's absolutely horrible to prove any theorem of second order approximation. I mean, to prove that the error is of order 2 in time or order 1 in space is absolutely horrible. So we limited ourselves to just prove that it is unconditionally stable. But for the accuracy, for the quality, I will just give to you some numerical experiments that prove that second order is really second order and first order is really first order. No mathematics behind this, because I think we can spend a lot of time, and I'm not sure to succeed. But this is fundamental, and I can see that I recovered the unconditional stability, which is the first one of the first goals of our work. Okay, so if you come back with me to the first order and to focus a little bit on this, we can see that I have to solve, once again, phase field, but phase field here needs R, and R needs phase field. So let me try to decouple this. To decouple this, let's look at the problem. You can really easy, it's really easy to, sorry, go back. It's really easy to combine and to take this quantity here and take this quantity equal to the rest and put it here. And if you do not mistake writing on the paper, you can prove that only one equation phi n plus 1 becomes this quantity equal Bn scalar. It is scalar. Bn is a vector, scalar phi n plus 1 multiplied by this. Gh is the operator identity or Laplacian. And okay, what you need to fix that to solve the phase field at n plus 1 delta t, new time step, we have to solve Laplacian or B Laplacian. But you have this scalar. This is not the function, this is the scalar. And the scalar contains the unknown itself. So what to do? Okay, the rest is not complicated because the rest, it is something that you already computed. If you start with the initial condition, this is easy to compute. Everything is easy to compute, except this is easy too because it is Laplacian or B Laplacian. I consider that you come with your favorite solver. So you have finite element solver. What is complicated is that in the same time, I have to solve this and this. There is one sympathetic idea is to think about some kind of splitting. Look at this with me, please. I'm going to consider that my unknown is going to be scalar product of Bn. Bn is given, is done, is computed from one time step to another. Phi n plus 1, phase field at n plus 1, it is the product scalar of itself by multiplied by phi 1 and phi 2. And the splitting I propose to do is to solve phi 1 as a solution of a part of the problem, solve phi 2 as a solution of the complementary, and then say that phi n plus 1 is equal to this. Okay, great. But if you write this, it means that you have to handle this quantity, but it's not complicated. Because if you remultiply this equation at left and at right by Bn, and if you work a little bit with the pencil, you can prove that this quantity is also Bn scalar phi2 n plus 1 over all this. It means, just keep in mind that to compute this, you need this. But this, it is already computed. It is the solution of this step. And then you can create this coefficient and it's done. So let's make some kind of sub-conclusion. You want to solve the phase field in the new time step? Okay, you can compute in parallel 1 phi 1 solution of Laplacian if you are with Alan-Kahn, B Laplacian if you are with Canillard. You can also do the same thing because keep in mind that n means that is the previous time step, so it is computable. Okay, you solve this, you solve this, you solve this coefficient thanks to 4.15. You recover your phi n plus 1, and you go ahead for the next time. Okay, to convince you that you are able to do the same game, to play the same game, but for another model. The model I show it to you, I present it to you, I call it MBA model. It's more complex model. It is a model for which the function here, it is applied in the gradient with B Laplacian. Believe me, we can replay, we can do it again using the same technique, the same scalar function, and nothing impossible to conduct. No bad surprise, let's say. Once you do it once time, you can repeat it for many times. Okay, now it's time to convince you that the scheme works well, and to do so, no more mathematics. We are going to simulate, and to simulate, I consider one particular case. I will solve the phase field solution of this model. I consider the derivative of the potential, energy potential given by here. This is something that we found with Alan-Kahn. I will cover GH equal identity and also Laplacian. I'm going to start with initial condition. I give to myself the initial condition for Alan-Kahn equal to this. For the gradient flow, Canillard is equal to this. I know nothing about the exact solution. So as you know, when you ignore the solution, what is the strategy? Is the strategy consists in computing a high approximated one. I mean, you take very small time step, you take very huge mesh, you compute, and you stop at what time, and you consider that at this time, this is the solution of reference. And after you change your time step and you compare by interpolation at the end with the reference solution, and you compute your error, and you see if you are first order or second order. We did it for this example. And as you can see, second order at left, second order at right, but at left, it is for Alan-Kahn. It means that capital GH, it was identity, and -1, which is Canillard. As you can see, everything runs well. You can see with me that the first method of GA and our method looks to work as good. Maybe a little bit better for large time step for our technique, because as you can see, when you go with alpha equal epsilon power 2, we gain for large time step, which is welcome information because the scheme is unconditionally stable, and we need to take large time step for unconditional time step. Okay, so another example. Now I keep the same model. I just fabricate the right-hand side corresponding to this exact solution. Okay, so instead of solving 0, you inject your right-hand side, and this comes from plugging this initial exact solution in the model. And I will compare my exact solution with the approximate one at time t equal 1. And once again, I play this with the second order. And okay, everything runs well. And I also added another way, it is Crank-Nicolson. We proved also an unconditionally stability theorem for Crank-Nicolson second order, and everything works nice. This is for Crank-Nicolson. what we did, we decided to play with epsilon. Okay, we play with epsilon, and we took alpha equal epsilon power 2 and alpha equal 0. Alpha equal 0 is the scheme proposed by GHM, and I mean, we can see, for example, for epsilon equal 0.0, mean that the smallest length of zone between solid and liquid, and you can see when alpha is equal to 0, the curve blue, when your time step becomes small, it is something not so good. I mean, you have a palier, stagnation of the error. And with our contribution, we see that we succeed even for this epsilon to have better result, and we can continue decreasing the error, which is the nice, let me tell you, that this is the added value of our method. It is quite efficient when the zone, when the length between solid and liquid, where the thermodynamics plays its role, it becomes nice. Okay, let's take more complicated example. Let's go back to MBA, the model with functional F, which is F, it is the derivative. Huh? F is the derivative. F, comment l'écrire? Petit f. This one is okay. Okay, we have two complex quantity with slope, without slope. Once again, it's complicated to have, since you put 0 here, it's almost impossible to have exact solution. So let's go with initial condition and apply the same technique idea to compare with the reference solution, obtain it with very small time step and very huge mesh. And this is with the slope selection, without slope selection, and we can see we have really good advantage for the new method, since it's better than the other, and the other correspond to alpha equals 0. Okay, so everything is welcome. Now I would like to share with you one strategy that I founded with my student in this reference. Okay, once you present a time scheme and you say that it is unconditionally stable, it means that you can choose by yourself the time step, and you can choose the time step and your objective is the time step to be as large as possible to end the computation rapidly. But at the same time, you want to be accurate. So if the accuracy push you to have a small time step, so let's go with any explicit time step scheme. Now, to save the idea that it is nice to have unconditionally stable scheme, this guy proposed to us, okay, let's go with, in the code, to decide that the time step is going to be the maximum between this quantity and delta max over this. So it means that every time I will choose the best strategy. The best strategy is the biggest time step. So I fix here maximum equals 0.01 and delta mean is equal 0.005. And as you can see, I start with to show this computation. This computation is made with alpha equals 0. And for alpha equals 0, please see that when you have delta t equals 0.01 and delta t equals 0.0, we don't have the same solution. Some kind of numerical diffusion comes to make things not so good. Or to say that maybe this scheme is not. Now, I would say another interpretation. Let's say that, consider that delta t is very small. Let's say that this is solved in the sense that we get enough accuracy because we are with a very small time step. This is delta t bigger. So it means we are approximated, but not enough. That's why the solution is not completely solved in the sense that once you compute with small time step, I have another solution. I mean, we say that we converge if I put delta t equal something smaller than this, and we keep the same behavior of the solution. It means that here, okay, I am solving, but I ameliorate my solution as soon as I decrease my time step, which is normal because we go to zero, the error go to zero with delta t go to zero. But if you apply the other strategy, we take delta and delta max, and you can see that for gamma equal 10, it is something that it is in the method, in the algorithm, and you see we have the same quality of the solution. Okay, so this is to end the first part. What can I say that in this paper published in Journal of Computational Physics, we improved the method presented 2 years ago by GSM. The main advantage is that this method remains robust when the epsilon and the other parameter also present in the model change and comes to be very small. So it is more accurate and more, let's say, like the fiability is much better than the previous one. And it helped us really to make some other numerical. I can show you, for example, this is something that we did it to solve. As you can see, this is don't-read problem, and the interface is solved using also phase field coupled with the temperature equations. And this is our first step to produce the other problem, which is the experimental simulations, experimental observation. It's absolutely wonderful. It's more rich, more complicated than the one I'm presenting with the numerical. But I hope that in few years, we hope we can try to make appearing all this complex topology. For the moment, as you can see, we are really far from this objective. But okay, we are here to progress, and a lot of work remains. But that's it. Okay, so we did it in 3D. As you can see here, we have a porous media. Inside the porous media, we put a PCM, the phase change material. And for instance, this is PCM. This material is the salt, natural salt. We hot it up to 500 or 600 degrees. And as soon as the salt changed from solid to liquid, I disappear the color blue. And what we call from the industrial point of view, the time of charge, it is the time, the real time, when we have no more blue. No more blue, it means that all material goes from solid to liquid. And this time of charge is very important for the industrial guys who are working in the thermal energy storage. This is the two simulation have been made using phase field model coupled with solving temperature equation. I think I have combien il me reste de temps, Nabil? Nabil?
10 minutes. 5 to 10 minutes. Okay.
Okay, I don't have time to go with the second part, but let me please show you something. We were very happy by the fact that we are able to solve the nonlinear part using an explicit scheme and to produce by the end an unconditionally scheme. And we know that for Navier-Stokes, we have several problems. If you want to solve Navier-Stokes that I present here, we have the velocity, we have the pressure, and we have the nonlinear term. And nonlinear term is something very complicated to solve. And usually we solve it using an explicit scheme or characteristic method. In this case, we have what we call CFL to respect. And especially when your viscosity becomes very small, you can say also Reynolds number very huge, the explicit treatment of the nonlinear term conduct us to fix a very small time step, and the computation becomes very cost. And one of the objectives is to try to propose a scheme explicit for the linear term and as unconditional stable as possible. So we said, okay, maybe we can apply the technique that I presented to you for the phase field, but for Navier-Stokes. And the idea comes from here. Let's consider this energy function, and it is the integral on the space of this quantity, some kind of energy. It is energy, and the auxiliary function is going to be RT as previous Racine carry of this quantity. You can convince yourself that this quantity, you can derive it, and you derive it in the sense that the derivative 2r dr over dt, it is this. Why it is this? Because one part of it is equal 0. U gradient u scalar u is equal 0, and why u scalar gradient u u is equal 0? Because divergence u equals 0 and u scalar n is equal 0. It's very classic result for Navier-Stokes. So the new problem reads, I keep the same thing. Please note that this is equal, this is over this is equal 1. Because this is exactly the definition of it. It is square ET. So I do not change from the continuous problem. I do not change the definition of the problem, except that when I'm going to the approximation, this is not going to be equal 1. It's going to be small to 1. It's going to be something that will start not 1 and go to 1. And you can run this method using the same technology than the one I proposed to you for the phase field, for the scalar phase field, but we preferred with my other student to go with another idea proposed by another group of Chinese and American. Instead of playing with energy, we learned a lot about this energy. We did some kind of let's say, machine learning. We learned about the behavior, and we said, instead of looking for this RT and ET, something can be equivalent is to go with this function. And this function, you can derive it. It's clear that derivative time is exactly this. And so you can prove, thanks to this relation that I mentioned for you, BUVV, it's the nonlinear term, it is U gradient U scalar U, or U gradient V scalar V. And when you are in this space and this space, you can see this quantity is 0. By the end of the day, you can prove that dq over dt is not only this, but plus this. And what I'm adding here is 0, thanks to this result. So now, the new problem of Navier-Stokes is going to the old one, except that I'm going to add all this quantity. This quantity, nu is the nonlinear term. This is, dear colleague, this is equal 1, because this is equal this. This over this is equal 1. Nu is the nonlinear term that you know in Navier-Stokes, minus mu plus mu is equal 0. So I do not change the definition of the problem, except that I put some quantity that I'm going to perturbate it once I will move to the discrete problem. What is mu? Mu, which is something like nonlinear term, but not with the unknown velocity, with some kind of given velocity. Okay, it's really some kind of technique that we succeed to put and to run correctly, because we learned a lot about our mistakes. So, okay, I'm not going to solve Navier-Stokes now, though the new idea is to solve this new problem. From the continuous problem, from the continuous point of view, it is exactly the initial problem, because this is 1 and everything goes well. So, except when we go to the approximation, I will perturbate all this coefficient, and I will play with one scheme which is close, very close to the initial one, except that the nonlinear term, as you can see, is solved with the explicit way, not implicit, explicit way. It is multiplied by one scalar, and the scalar has to be updated thanks to the scalar equation, which is complicated to solve. And I'm not going to go far. this is the second order version, but this is the wonderful result that we proved that by the end we have an unconditional time scheme, an unconditional time scheme. This is an unconditional time scheme. It means that you can take any time step and your scheme will run, you will converge, and the accuracy will be related to the choice of time scheme. But what is very amazing, it is unconditionally stable, but the nonlinear term here is solved in the explicit way. This is very interesting this is it's a very interesting evolution of the way to solve Navier-Stokes. And as a practitioner, with my colleague here in the lab, we are very happy to play to use this new scheme because we are able to produce many results and to decide that we chose the time scheme small because we want accuracy, not because we want to satisfy the stability of the scheme. But you know better than me that this is obvious. Okay, all this are the proof. Maybe I don't have time to discuss with you all this detail. I was very optimistic regard to the time that I'm going to use.
You can have more time, Mejdi, if you need 5 minutes.
Okay, maybe so I can show you one result. This is, I used to say to my student, when you start validation, please do not hesitate to consider a very, very, very easy case. Easy case because when you consider the velocity divergence free, this is divergence free, divergence velocity, it is 0. The pressure is first order. The finite element I'm going to use, it is P2, P1, it is stable for Stokes part. And it means that we reduce the error space to 0. So we can, by the way, control all the rest of the error. And you can see here the quality of the error when we change the viscosity. Viscosity equal 1 equals Reynolds equal 1. And you go to viscosity equals 10 to minus 3. And you can see here, we have two results here. Here we have result with the no contribution of one idea, which is U start equal, I can show you, this is the quantity here. This is a new idea we add to this one. This is also another idea we added. And it means that sometimes to time, you can add a treatment of the nonlinear term with the semi-implicit way. And this, if you don't do this, mean here 0, for viscosity equal 1, everything goes well. If you don't use this and you make small the viscosity, I mean, Reynolds becomes important. The fact that you do not solve sometimes to time with a semi-implicit way your nonlinear term, make that your pressure is bad, your velocity is good. And with this new modification, you have nice velocity, nice pressure. For me, nice, it means not only the level of the error, but also, and certainly the fact, for example, that here you divide it by 10, your error is divided by 10, and so on. Here it's not the case because we have a limit of the space conversion, space representation. Okay, I think I'm going to stop here, okay? Maybe I will have another opportunity to speak with more detail about Navier-Stokes. And let's keep just in mind the fact that phase field model is really nice to face physical problem comes from phase change material. As soon as your interface, as soon as your interface contains some physical phenomena, do not hesitate to go with phase field modeling. And once you fix your mathematical model, think that you have many possibility of schemes in the literature. And one of these schemes is the one I presented to you. And what is the advantage? I'm considering very positive that your scheme is not good only for one choice of epsilon or tau or some parameter. It looks stable and strong in the sense that able to be stable and quite accurate. When your interface is sharp, when your parameter of physics is very small, which is very complex, and usually the other scheme, they fail, and they do not succeed to provide a good result. From this point of view, I think that the scheme had an added value. If you want to go with Navier-Stokes, which is another, we go from scalar to vector. There's a possibility also to adapt this kind of technique of auxiliary scalar variable, but you need really to be clever and to put the right parameter in the right place to succeed to converge with unconditional stability and quite accurate result. I hope my talk was giving you some new information, and I'm waiting for a question to complete my presentation. Thank you, Nabil. Thank you, everybody.
Thank you, Mejdi. Is there some questions? Fathi, yes, Fathi.
Assalamu alaikum. Thank you, Professor Nabil. Thank you, Professor Mejdi, for a nice talk. Although I joined you 15 minutes late, a bit involuntary. Thank you for a very nice presentation. Although, as I said, it was a bit. I was a bit late. The techniques are very nice. I have worked on the Navier-Stokes equations about 2000 and 2001 and 2 with another professor, Najib Smawi, in Kuwait University, and we have tried to look at it from a connection with the Hopf-Kohl transformation, and we transformed it back and forth to the convective diffusion, periodic parabolic convective diffusion equation. And in this way, basically the parallel, because the convective diffusion equation is like a state equation, etc., has been like studied a lot. So there are lots of dynamics and lots of ideas that basically you can pick up, and then you translate them into the Navier-Stokes equations. And in other words, you can get a lot of dynamics through this kind of translation. So I put the 2 papers in the chat. I've sent you the 2 papers, and I really appreciate the techniques that you have approached. The other thing I want to talk about is the epsilon square that is at the beginning of with the Laplacian. That basically when it goes to 0. So this is like an interface. You can, there is some techniques with the Sumudu transform. I've considered this actually with some Turks before, but it did not go far because we were not able to pursue it due to Corona, etc. But if you look at the Sumudu transform, actually you can apply the Sumudu. Unlike the Laplace, you can apply it many times. And then if you can apply the inverse Sumudu, because it divides things by n factorial, then actually you can look at these transforms as the epsilon is going to 0. In other words, through this transform. So this is maybe an idea that we can investigate at some point. I'm just throwing it there, but I have not more to say, but thanks very much for the nice presentation.
Thank you for your comments. Thank you.
Thanks.
Is there other questions?
Nabil, I send you my slides. Do you want to have my slides? Or?
Yes, of course, yes.
It would be nice, yeah.
Yes, I generally put the slides on the website of the webinar.
Okay.
And
if you don't mind, Nabil, if you can send them, I can put them on the groups, on my groups.
Thank you.
I can send them on my groups.
Of course, yes.
No, I mean the idea is sometimes when you put them on the site of the webinar, then not very many people have access already. Some of the people that are not present, I would rather put the slides on the group itself. The link at least. Yeah. Okay. Jazakallah khair. Thanks.
Okay, Fathi, can you send me the 2 papers you spoke about?
Yeah, I have put them in the chat. I have put the links in the chat, and I will be happy to send you. And I have put my email.
I will find it in the chat, no problem.
Yeah. And also I have sent you my email, so I'll be happy to communicate more about them. Inshallah.
Okay.
Yeah. Okay. Most welcome, my brother. Thank you.
Thank you.
Mejdi, just a basic question. For your model, you have a nonlinear equation and you split when you linearize when you split the operator, you split such a way that you have an implicit scheme, okay, unconditionally stable scheme. Is it the motivation of, or there is another idea that lead you to make this split?
Okay, thank you. Thank you for the question. Okay, let me rapidly consider. Excusez-moi. We have two main problems, Nabil. When you solve, imagine that you want to solve this equation, okay?
Yes.
And if you come with this equation, the quantity here is very nonlinear. Okay. As I showed you before, tu as des choses with the gradient, it can be very complicated.
Yes.
It can be also modest. But everybody would like to propose a scheme for which this part, it can be solved implicitly, Newton algorithm, big gradient. There is one technique very famous, which consists and consider and show capital F majuscule. You can decompose the concave, convex part. You can implicit the convex, explicit the concave, and you can show that the scheme is unconditional. So we have many ideas.
Yes.
What is the goal here? The goal first is to propose something for which you can make this part explicit. It means you will never solve it.
Okay.
You start with phi0, you compute the phi0, the nonlinear contribution, and you put on the right-hand side. And by the end, you have just to implicit the Laplacian. But you have a code. Everyone have infinite element, spectral element, I don't know, to solve this problem. It's not complicated to solve implicitly this. The problem of our method, it was that once we get this idea, Nabil, rapidly, sorry. Once we get this idea here, we see that, okay, great. I prove mathematically that this is explicit. I multiply this by this scalar. I make some kind of work sur le papier to finally discover that I don't need to solve R. No, I have to solve the question in the phase field. But the question of phase field, it's everything is explicit, especially the nonlinear term. But I have this coefficient. Ça, c'est un scalaire. But this scalar needs to know the solution. And the idea comes from, okay, let me solve one. Let me say that my unknown will be the sum of phi1, phi2 plus this coefficient. Et après, tu dis, I have to choose. I have many choices. Let me solve phi1 qui est là. This part is part of, sorry, this part is part of the problem. I will take one phi1 to solve this with this, and one phi2 to solve all the rest with this.
Right.
If I add both, it's not enough. So my global solution is going phi1 multiplied by this plus phi2. C'est d'où? C'est une astuce.
Okay. Okay.
Et après, once you say this, okay, my God, this is a total implicit. This is implicit. Mais ça, c'est, if you are with Alan Kahn, this is identity, it's at Laplacian. And this is Laplacian. So we can solve in parallel to Laplacian. And after you can see that avec un stylo et un crayon, you can convince yourself that this coefficient can be also computed explicitly thanks to the 1 and the 1 you already computed in parallel. So I compute phi1, I compute phi2, I make a scalar product of all this, and I construct the coefficient, and I go ahead.
Okay, okay. Is there other questions, please? No questions? Okay, thank you very much, Mejdi.
My pleasure.
For this presentation, and we hope we will have you again in this webinar. Okay.
There is another part of my activity that my friend and colleague Thomas Chacon will present to you, I think, in a few time.
Okay.
It's about
thank you, Dr. Mejdi, for your presentation. Good presentation. for our physical, and inshallah it can be applied for different domain.
J'espère aussi.
Inshallah.
I hope, yes, I hope to, of course.
Oh. Yeah. I have noted that Carlo Catani is here. MashaAllah. So, welcome, Carlo. Carlo Catani.
Nice to meet you and to see
Yes,
you.
it's here to hear from you. Yes, great. From Italy. Yes.
You're welcome.
Thanks a lot. Thanks a lot.
Yes. Yes. Okay. Miss you, Carlo. Bye.
Thanks. Bye.
Great. Great, Nabil. Jazakallah khair. And Mejdi for this nice
See you
presentations.
for the next webinar. Mejdi,
Yeah.
I propose that I finish this session and I will restart another one 5 minutes later.
Okay, with the same link?
Yes, with the same link.
Okay.
Okay.
Okay. Dans 5 minutes.
Tahar, tu...
Yes,
Okay, I will stop.
Are you saying there is...
Oui,
Nabil, are you saying there is another something?
No, it's not a seminar. It's just an informal discussion with on a research project.
Nabil, le temps de boire un café, je reviens.
Okay, so are we invited or... We are not invited. It's not for the public. Yeah?
No, you are not invited. Yes.
أنا أتكلم فيك. Yeah, okay, thank you. يعني it's not for the public يعني لأن I did not know about it.
Yeah, I'm sorry. Yes, it's not
Thanks.
for the public. Yes.
Yeah, لأن I distributed يعني I distribute your webinars, you know, for other
Yes,
people.
of course.
I just wanted to know.
Everybody is
يعني,
welcome, of course. Thank you, Fethi. Thank you, everybody, and see you next time.
Bye.
Okay, مع السلامة. Bye.